And this lecture is about B trees. B tree is an indexing technique that helps to facilitate the data retrieval, storage, and searching faster. B trees is different from the concept of binary search trees. B trees are basically not binary trees. These are balanced trees, and these are known as balanced trees due to the reason that all the leaves in case of a binary tree are always on the same level. So the basic motivation behind using B tree is that when data doesn't fit in main memory, then it is stored on the disk, and a typical disk operation is 2 lakh times slower than a memory operation. So if the data resides in the main memory, then it can be retrieved 2 lakh times faster compared to a disk retrieval. So a disk access is too expensive compared to a typical computer instruction, due to the reason that hard disk has a mechanical limitation. So in case of large files, this number of disk accesses becomes important. So if there are too much operations that requires the data to be retrieved from the secondary storage, then this operation may cost a lot more instructions compared to memory retrieval. And this typically happens for the data that is too large and can't be fit in the main memory. So if the data structure or if the file can reside in the main memory, then there is no issue. But for the large files, like database files that have too much data and may reside on the secondary storage, there in such cases, the retrieval may become critical. As we know, secondary memory is typically divided into equal size blocks, or these are also called as segments or pages, which you may have read in operating systems as 512 size blocks, 2048 or 4096 bytes blocks. So when we retrieve a data from secondary storage, then it is retrieved in the units of these blocks, segments, or pages. So if you want to retrieve some data from the secondary storage, then you can't read a typical byte, but instead a complete block containing the typical byte that you need may be transferred from the secondary storage towards the main memory. So the basic I operation transfers the contents of one disk block from or to RAM. So the unit of transfer between the unit of data transfer between RAM and secondary storage is typically a disk block or segment or a page. So our goal is to devise a multi-way search tree, also known as B tree, that will try to minimize the file accesses by exploring disk block reads. So as we minimize the disk block reads, we improve the retrieval time of the data. So as much disk block reads as we have, the overall system will slow down, or the overall file retrieval system will slow down. B tree is also known as multi-way search trees. When we call a search tree a multi-way search tree or B tree of order M, then this means that a node in a B tree can have at most M childs. So it's a generalized, B tree is a generalization of binary search trees. In case of binary search tree, we have at most one key per node, and a node can have at most 2 children per node. While in case of B trees, we can have more than 1 keys per node, and the number of children would be 1 plus the number of keys in a node. So let's suppose if we have k number of children, then the number of keys in a node having m children would be k minus 1. So as you see, in case of binary search tree, there is a single key. So there are 2 childs, one on the left and one on the right. So similarly, if we place 3 nodes sorry, if we place 3 keys in a node, then or 2 keys in a node, then the possibility is to place 3 branches. So similarly, if we have k keys in a node, then we can have k plus 1 child of that particular node. And importantly, as like binary search trees, this tree is also ordered. So data is sorted in case of binary search B trees as well as in binary search trees. So we see in case of binary search tree, we have a single key. So in case of single key, we have 2 children, one on the left and one on the right. But if there are more than 1 keys, like for example, if there are 2 keys, in case of binary search tree, we see that we have 1 key and 2 children. So children are always 1 plus the number of keys in a node. So in case of binary search tree, if we place 2 keys in the node, then we will have 3 children. Or if we place 4 keys in a node, then we will have, 3 keys in a node, then we will have 4 childs. So the number of children's would be 1 plus the number of keys in a particular node. So this branch would have all the keys. The branch on the leftmost side would have all the keys that are less than this this key, the leftmost key, while the nodes, while the keys in the branch second from the left would have all the keys that are between the 2 left entries in a key. So similarly, like that, like this example, we can see that this is a node at the top which has 5 keys, K1, K2, K3, K4, and K5. All the values in the left branch have the keys that are less than K1. And all the keys in this particular branch will have all the keys that are greater than K1 but less than K2. Similarly, we can see that a branch between K2 and K3 would have all the keys that are that have their values greater than K2 but less than K3. And similarly, the last branch would have all the keys that are greater than K5. So as we have already discussed, M defines the number of children that a B tree can have, at most can have. So a B tree of order M is a M-based search tree with M children. So B trees are balanced search trees designed to work well on direct access secondary storage devices. B trees are similar to red-black trees, but are better at minimizing the disk I/O operations. So basic purpose of B trees is to minimize the disk I/O operations and are typically used and are famous with databases. If you have worked with MySQL or SQL Server, then when you create the tables, you can see there are options to define the indexes using B trees. So these B trees can boost the performance of a query or a table from hours to even seconds. But if you carefully define the indexes using these B trees. And definitely all the leaves are on same levels. That's why we call these as balanced trees. So this is one of the typical example of B tree in which you can see that the root node has 1 key, so it has 2 children. On the other hand, at the second level, we have a node with PH keys. So there are 2 keys, D and H, so it has 3 children. Similarly, at level 2, we also have a node with QTX. So there are 3 keys and 4 children of this particular node. And we can see that the branch on the leftmost side of Q has N and P, which are less than Q. Then a branch between Q and T has R and S, which is in between Q and T. Then a branch between T and X have V and W. So V and W are greater than T but less than X. And finally, the last branch has Y and Z, which are greater than X. So the data is sorted in case of B trees. And this is a typical binary search trees, which we also have seen in the previous lectures. So if we define a B tree using this data given in binary search tree, so we may have a B tree of height 2 or levels 3, a B tree of height 3. So in this case, what would be the difference? As we have already discussed that when we transfer a data from secondary storage device to main memory, then it is transferred in the forms of disk blocks. So in this case, if we retrieve the data and each node represents a disk block, so at most we have to retrieve 5 blocks, as the longest branch contains 15, 6, 7, 13, and 9. So this is the longest branch which has 5 nodes. So there could be possibly 5 disk block reads in the worst case. On the other hand, we see in the B tree that it would require at most 3 disk block reads as the height is 3. So if we assume again that a disk read is 2 lakhs times slower than a memory read. So if we justify the cost of a disk read in the form of 2 lakh instruction, so these 5 would require approximately 1 million instructions time. On the other hand, in this case, as we have to retrieve at most 3 disk blocks, so the time would be approximately 0.6 million instructions. So these are the few important properties of the B trees. B tree is a rooted tree with root T with the following properties. Every node has the following fields. Nx, the number of keys currently stored in X. So this would be an integer value that would define how much keys are currently stored in the current node. So if we see in case of this example, so the root, in case of root node, Nx would be 2. In the case of all other nodes, Nx would be 1. As all other nodes have only 1 keys in them. So Nx would be 1 for all the nodes except the root node, which would have Nx as 2. Then every node also has the keys themselves, as we have seen in a previous example. Nx would be 2 in the root node, but the values themselves would be 6 and 15. For the node containing 3 would be a value, but Nx would be 1. Similarly, 9 would be a value itself, but Nx would be 1. So there would be an Nx and the keys themselves in the ascending order. Another flag would also be present in the nodes of the B trees. This is would be a Boolean flag that would represent whether a node is a leaf node or not. So in all the nodes at level 1 and level 2, leaf of X would be false, while for all the nodes at the bottom level, leaf of X would be 1, as leaf of X would be 1 or 2, as all the nodes at the bottom level are the leaf nodes. So if X is if we call X as any node that is an internal node, then it also contains Nx plus 1 pointers to the children. Or in other words, if a node X that would contain nx keys, then it would has nx plus 1 childs. Leaf node doesn't contains any children. Definitely, we all know that leaf node has no children. The keys key I of x separate the range of keys stored in each subtree. If k1 is any key stored in the subtree with root c1, then k1 is again this point 3 justifies this diagram that we has already discussed in detail, that all the keys on the leftmost branch k1 at the leftmost side of k1 would have all the keys less than k1 and so on. So any branch would have the keys that are larger than the key in the root node and would be smaller than all the would have all the keys that are smaller than the key on the right side in the root node. Finally, as these are balanced trees, so each leaf has the same depth, which is the height of the B tree. Then there are lower and upper bounds on the number of keys a node can contain. These bounds can be expressed in terms of fixed integer t greater than or equal to 2, called the minimum degree of a B tree. Always remember that the minimum degree of a B tree is t, and it should be greater than or equal to 2, that it should be at least with a value of 2. Why t can't be 1? Think yourself, why it can't be 1? What if you set t equal to 1? More importantly, as we have already discussed, m is the degree of a B tree, and it defines that how many children a node can have in the maximum case. Now, in order to understand further the B trees, always remember that a node can have at least t minus 1 keys in a B tree and at most 2t minus 1 keys in a B tree. I repeat again, a node can has at least t minus 1 keys and at most 2t minus 1 keys. In the minimum case, a node can has minimum t children and at most 2t children. So m is always equal to 2t. So these are the few properties that you should note down and remember. A node can have minimum t minus 1 keys and minimum t children's and at most 2t minus 1 keys and at most 2t children's. 2t is equivalent to m. And these conditions definitely doesn't apply to a root node. A root node can has minimum 1 key and maximum 2t keys. Sorry, 2t minus 1 keys. If a node has 2t minus 1 keys and we have another key to insert in that particular node, then we can't insert a new key. Rather, we will split the node into 2 nodes and then we place the new key in the sorted order where it lies. So the question is, what is the minimum height of a B tree with n entries? This question is important because the maximum height of a B tree will give an upper bound on the number of disk accesses. So this is the formula to find the height of a B tree with respect to the degree t. If the minimum degree t is greater than 2, then we can substitute the values in this equation to find the height of a B tree. For example, if we have 1 million nodes, 1 million keys, then we will replace n with 1 million, and let's suppose the minimum degree of the B tree, which is t, is 3. Then this would be log 3 million plus 1 by 2. Now this is a B tree of height 3 containing minimum possible keys. So as we have already discussed, minimum keys that can reside in any node of the B tree is t minus 1, except the root node, which can have at least a single key. So at the top level, we see we have only one node, so only one key and a single node. So as we have a single node, it would have at most 2 children. So at the next level, we see 2 children. And as there are 2 children at the level 1 and each children has t child, so at the next level, we will have 2 t childs. Similarly, at the subsequent level, we will have 2t into t childs, which would be 2t square. So the number of nodes is minimized when the root contains only one key and all other nodes contain t minus 1 keys, 2 nodes at the depth 1, and so on up till 2t squares. So at depth there is a general formula. If we see these numbers at the right side, we can define that at height h we have 2t h minus 1 keys, 2t power h minus 1 nodes. So at depth 3, we see that we have 2t h minus 1, 3 minus 1 is 2. So we have 2t square nodes at level 3. This you can skip at the moment. There is a numerical example for n equal to 2 million. Let's suppose we have 2 million keys and we have m equal to 100. So the maximum height of a B tree of order m will be only 3, whereas a binary tree would be of height larger than 20. You know the formula to find the height of a binary search tree. For B tree, we will use this equation to find the height of a B tree. Here we have n as 2 million and m equal to 100. But this equation requires n and t to find the h. So n is 2 million in this case. What would be the t? As we have already discussed, that m is equal to 2t. So m is given, which is 100. So using m equal to 2t equation, we can find the value of t. As m is given as 100, 100 is equivalent to 2t. So definitely t would be 50. So log 50, 2 million plus 1 by 2 would give you value 3. So the height of the B tree would be 3. Next, these are the few operations on the B tree: searching a B tree, creating an empty B tree, splitting a node in a B tree, inserting, deleting. So searching is much similar to a BST, but the only difference is that rather than searching two-way right or left, you have multiple options to search. And definitely the tree is ordered. So if you go through the value in a node and find that the value you are searching is greater than this particular key, but the smaller than the next key in this node, then you can go to the sub branch in between them. So in other words, at each internal node x, you have an nx plus 1, where nx is the number of keys in the node, nx plus 1-way branching decision rather than the 2-way branching decision, which is in the case of binary search trees. So B tree search takes as input a pointer to the root node x of a subtree and a key k to be searched. And this searching operation is typically similar to the binary search tree operation. However, if we discuss the time, the number of disk page accesses produced by this procedure is order of h, which is, as per the equation seen for the height of the B tree, is O log n base t. Since we know that the number of keys that a node can have is less than 2t. So thus the time taken to search within each node is order of t, as the maximum number of keys in a node is 2t minus 1. So it would be order of t, as we omit the constants and the constant values. And the total CPU time is order t cross h. Why t cross h? H is the height of the B tree, which we may encounter in the worst case. So that's why order of h, and we know from point 2 that order of h is order log of n base t. So that would be log n base t, and the time to search within each node is order of t, as there are at most 2t minus 1 keys. So that's why it's t cross h, where h is the height of the B tree. So h represents the time to move across the nodes in a B tree, and t is the time to search within each node of the B tree. Total time is order of th, and finally it's order of t log n base t. Now splitting a node in a B tree can be done in two ways. So inserting a key in B tree is significantly more complicated than inserting a key into a binary search tree. Fundamental operation used during insertion is splitting of a full node y, having 2t minus 1 keys around its median key ki, key y into two nodes having t minus 1 keys each. I think before explaining these 2 points, let's discuss an example, then we can discuss this one. So this is an example of a splitting. Let's suppose you have a node that contains p to v values, and a parent node of this node that has n and w values. Let's suppose this node is filled and we want to insert a new key in this node. So if you want to insert a new key in this node, firstly we split this node into 2 parts. So these 2 parts would be then PQR and TUV, the middle value S will move to the parent node. And let's suppose there is a new value that we have to place. So we will find the appropriate place in either the left side node or the right side node. Let's suppose if we want to place the y, then we can place the value of y in the not y. And let's suppose there is some value, let's suppose t1, then we can place that t1 after t in the right node. Let's discuss an example, then I can explain these points. Let's suppose this is a B tree, and the minimum number of keys at any internal node is t minus 1, equal to minimum degree of a B tree is t. And the minimum number of keys, t is 3 in this case, and the minimum number of keys in each node can be 2, and the maximum number of keys at any node can be 2t minus 1. So it would be 2 into 3 minus 1, which would be 5. So let's suppose for the given tree, we have to insert the B. So a node can have minimum 2 keys and maximum 5 keys. So the appropriate place to place the B is in this branch, which contains A, C, D, E. So as there are 4 keys and another can be accommodated, so we place B in the appropriate sorted order in this particular node. Then let's suppose we want to insert the symbol L. Again, the node can accommodate this L symbol, no issues. Then we want to insert F. Now, now this is a tricky one. In this case, the node F can reside in the leftmost node along with A, B, C, D, E. But the issue is that the node is already filled. It has already 5 keys, and the 5 is the maximum limit as defined by the T. 2t minus 1 is 5. So before placing F, we have to split this node into 2 parts. So one part would contain AB, other part would contain DE, and C would move towards the parent node. So A, B, D, E, and the C would move towards the parent node, and then we'll find the appropriate place for F, and F would be adjusted along with D, E, F. And as C move upwards, so there would be another pointer that would point A, B, and a pointer that would point D, E, F. Similarly, then try what will happen if you insert T. And after that, try to insert Q. So there would be another splitting, and it may increase another level of B tree. So why these are balanced trees? Because this tree grows upward rather than downwards. BSTs grows downward, but the B trees grow upward. So all the leaves remain at the same level. Then before this, in these slides for insertion, we have discussed two techniques. One technique is as we go from top to bottom to find the appropriate place to insert a new key, we can split any node that we encountered as failed. So if we find any node that is failed while moving from top to down to insert a new key, we split that node. So advantage is that we have that we can avoid another pass of splitting in the other approach, where we go downward, then we find a node that is failed and we split this one and move one key towards the parent. And if the parent is failed, then we again split this node and it may increase the height of the B tree. So there are two passes in a typical approach, where we go downward, find the appropriate node and start splitting upward, as we have done in the example. Another alternative is that as you move downward, and if you encounter any node that is already filled, you split it down. So this approach avoids a second pass toward a second upward pass, but the issue is that it may result in unnecessary split operations. So two approaches. One is when you encounter a node that is filled, then you split it and move upward. So this would require two passes, but this would avoid unnecessary splits. In one pass in approach with one pass, you may avoid the second pass in a B tree, but this may result in unnecessary splits. Further, if you have any questions regarding this lecture, you may ask on the WhatsApp group.